So the situation is there's four, they called them, four rods. And then there's these black pucks. And they're sliding towards the rod, and the surface is frictionless. And we're asked to first off determine in which of these cases is momentum conserved. So is momentum, linear momentum, is that conserved? So is linear momentum conserved in these four cases? So guys, the first part of this is you have to be a little bit careful. The answer is momentum is conserved in this case and in this case, but it is not conserved in this case and that case. Momentum is conserved for case B and case C, not conserved for case A and D. Can anybody explain why?
Triangular.
Linear. Linear momentum is not conserved in those two cases. Go for it.
If there's an outside force,
There is an outside force. What is the outside force?
the axle.
The axle. So it's important, guys, that you remember there is an axle in the middle of the thing here. When this puck collides with the rod would go sliding backwards. But it doesn't because that axle stops it from moving, right? Well, how does the axle stop it from moving? It exerts a force. Not torque, a force. It exerts a force. There's a force from the axle on the rod.
So would the puck not bounce off if it gets directly?
It says, well, probably in the real world, but in physics world it says that it sticks.
Okay.
So yeah, in the real world definitely would bounce, but and so momentum isn't conserved because there's an external force on our system. What about in case D? You can make the same argument here. The rod, the would go sliding backwards. It's a frictionless floor, remember? The rod would go sliding backwards, but it's stopped because there's a force exerted by the axle. And so there's an external force, therefore momentum is not conserved. In cases B and C, there's nothing to exert an external force. There is no friction. We were told there's no friction. So there's no external force. And if there's no external force, then momentum is conserved. Boom, we're done. So it's conserved in those cases, but not in cases A and B. Now, the next question is, what about angular momentum? L, is that conserved? And the answer is, it's conserved in case A, check. It's conserved in case B, it's conserved in case C, and it's conserved in case D. Can anybody explain how that could be possible if linear momentum is not conserved? There's an external force on the system, so why doesn't that change the angular momentum? So, based on what you're saying, it sounds like you're defining the system to just be the rod, and you're saying that the puck exerts an external force.
No, the axle makes the puck an active torque instead of just a force.
Yes, but, correct. But our system, I'm defining my system to be the rod and the puck. So then any forces that they exert on each other are internal to the system, and those don't change the momentum. And so that's all well and good, but what about the force from the pivot? Why doesn't that change the momentum?
Because the distance from the center of rotation is 0.
Yes, the force here is being exerted at a distance of 0 from the axis of rotation. So it is an external force, but it's not creating a torque. And so yes, there's an external force on the system, but there is no external torque on the system. If there's no external torque, angular momentum is conserved. Does that make sense, guys? Thumbs up or thumbs down? Good, okay. So moving on. The next thing we have to do is rank. rank the momentums. And so here's my ranking, and here's the argument. Your ranking should be A is less than D is less than B, which is equal to C. That's the correct ranking here. And the argument is B and C, those have to be the biggest. Remember what we're ranking here. What we're ranking here is the rightward linear momentum after the collision. And so in cases B and C, the momentum after the collision, we said it's conserved, so the momentum after equals the momentum before. There's no external forces, so they don't lose any momentum. So they have the same linear momentum that the ball initially had. Case A has zero momentum after the collision, right? It lost it all. The puck comes to a stop, boom, hits the rod and it stops. No momentum is left, so that's the lowest. That's case A. And then case D does lose some momentum. The puck will slow down, but the puck doesn't come to a dead stop, right? It's going to keep spinning as the rod rotates. So it doesn't lose it all, but it is going to decrease some. So that's our ranking for that. You happy about that? Any questions? And then here's the ranking for the angular momentum. We have to rank the clockwise angular momentum after the collision. And A and C are equal, but they're the smallest because in those cases, there is no angular momentum. It's zero. B and D are equal to each other. They have angular momentum, and we said it was conserved, so same before and after. Let me go make sure we understand. In case A and in case C, there's no angular momentum because the puck is traveling towards the rotational axis. So it has linear momentum, but no angular momentum. Cases B and D, we're some distance away from the rotational axis. So we have angular momentum. Questions? Guys, I will unlock the assignment in your OneNote after class today. If you want to change your answer, you have an opportunity to do that. We're going to go ahead and I'm going to do something that's going to say something here that's going to make everyone very, very sad. Because we're going to take the last notes we're ever going to take.
I'm so sad that I just can't control
He
myself.
can't control himself. Guys, after today, we are done learning new physics.
Oh,
Then we all are-
that's devastating, Mr. Jones.
I have no more physics to teach you.
When are you going to teach us the mega equation?
The one mega equation that solves every problem?
Yeah.
I even got a secret. You have to take AP Physics C.
Wait, so we're going to learn that in Physics C?
Yeah, take Physics C.
Bro, that's 2 more years.
Wait, what? Why can't we just learn it now? Make everything
Why can't you just write it on the board?
I need those 2 years to come up with it. 'Cause it doesn't-
Oh, okay. I was legit thinking he had one.
No, there's no single equation.
Oh man, no there is. Yeah, just look it up. The old mind science guy.
So guys, the very last topic we're going to go over is rotational kinetic energy. And then I will be done teaching you physics. You're on your own. Yep.
After this, you're like not coming back to the classroom?
Interpersonal studies.
You won't see me again.
Interpersonal studies.
Yeah, tell Physics C.
I'm going to have my N64 set up in the back. I'm going to play games. You guys got to study physics.
In the games.
Review for your AP exam. And by the way, speaking of the AP exam, guys, if you're planning to take the mock test and you've not answered the poll on It's Learning, please do so. If you don't answer that poll, I won't print you a test, and then you're going to show up on the day of the mock exam and say, I'm ready to take the test, and I'm going to say, well, no, you're not, because there's no test for you. You can imagine-
Got him.
Got it. You just got Jones.
You just got Jones, that's what I'm gonna say. You've been Jones. Go
I
home.
just got.
Go home. Contemplate your life choices.
Oh, dang it, gonna have to go home on
Dang it, and I
Saturday.
got Jones.
Can we still get the pizza for show?
Yeah. Just gotta show up late.
It's just to be clear, it's just one pizza, and I'm cutting into slices. How many people show up? That's how many slices I cut it into.
All right, no one show up except for like one person.
All right, so guys, objects in linear motion have translational kinetic energy, possibly, which is 1/2 mass times velocity squared.
Give me a moment.
And you guys could probably, or some of you I'm sure have already guessed, objects in rotational motion, they have rotational kinetic energy. What do you guys think rotational kinetic energy might be equal to?
1/2
Hey, let's see. 1/2 I, 1 squared. Easy enough. And I'm going to tell you guys now, this equation is on your formula sheet. I don't think I've ever seen a AP physics question that requires you to actually use this formula. You are required to know that rotational kinetic energy is a thing, but I've never actually seen them have you calculate it.
So then really required.
Yeah, you just need to know the concept. The actual math isn't that important. And the reason why is because in AP Physics 1, we don't cover rolling. You don't cover rolling? You need this if you're going to talk about rolling.
This is my last physics I've ever taken.
So guys, look at the formula though. Guys, pay attention to the formula here. 1/2 I omega squared. It depends on an object that's rotating. It has kinetic energy that depends on its moment of inertia and how fast it's rotating.
Do tires roll on the ground or do they rotate on the ground?
So rolling is a combination of rotation and linear motion.
Take AP psychology.
So a tire is both rotating and moving linearly.
Okay.
And those two motions, when you're rolling, those two motions are what we call coupled. They're connected. The faster you're rotating, the faster you're moving linearly. So they're coupled together. Ideally, now if the tire is slipping, then they're no longer coupled. Right? If you're burning out, then the tire might be spinning very fast and there's no linear motion. But guys, let's see if we understand the important concepts here. An ice skater spins with an initial angular velocity. She's spinning, she brings her arms and legs closer to her body, reducing her moment of inertia by 1/2. What happens to her angular velocity? Does it A, stay the same, B, half, C, double, D, quarter, or E, quadruple? Take a second to think about it. What do you guys think the answer is? Okay.
What is the inertia equation?
So I'm seeing a lot of C, it doubles, that is correct. Can somebody explain why
Dubs.
this doubles?
Dubs.
Xavier, would you-
Well, I have explained. I just looked at the formula for angular velocity, and I saw that what's the sign in that formula? What is that for?
Which formula? What's the formula?
For angular velocity.
Well, we got a few of them.
The one that was wombo equals sine or delta sine divided by delta t.
delta like this.
Yes, or yeah, theta, not sine.
The theta is the angle. So that's like the definition of Wombo.
Okay.
And so those formulas, that's kind of how what we say Wombo is. It's the change in the angle divided by the change in time. We can't necessarily use that here because Wombo is changing in this problem. And this is when Wombo doesn't change. This is constant velocity.
Okay.
And so we have to use something that will apply when Wombo is changing. Can anybody make an argument that Wombo has to get bigger?
Come on, Steven.
Well, if the inertia gets cut in half, then that means it's not starting to move, right?
Yes.
So if it gets cut in half, the moment of inertia, then wouldn't that mean that the angular velocity doubles?
So it would, you're on the right track here. If I gets halved, then the angular acceleration would double if there was a torque. Is what you're I think what you're saying. But we're not talking about, as far as we know, this wasn't accelerating until she moved her arms.
It's because since they have to have the same final, like, they have to have the same momentum, when you increase, if you decrease the inertia, then the angular acceleration the angular velocity has to increase since it's I times angular velocity to get momentum, if the momentum is the same. then
Yes,
the
exactly. Do you guys remember last week when I was spinning in my chair? That's what this is. When I was spinning in my chair and I had my legs out, I was moving slow, and then I brought my legs in and I spun up. Right? It's the same thing here. So
Can we
guys, I
have a
think one trick
demonstration
you can
again?
use, you can't necessarily always get the answer this way, but something you can do is increase your odds of getting the right answer. You can just think back to me spinning in my chair. And in fact, I often think back to me spinning in my chair. And you can think back to that, and you can dwell on that pleasant moment. And you can remember that when I brought my legs in, I started spinning faster. And that
Mr.
immediately
Jones.
tells you this, and this are wrong answers.
Can we have a reenactment?
Yes, we can, maybe if we have time. So that leaves you with C and E, and then at that point it's a coin flip, right? And a coin flip isn't bad odds if you're taking the AP exam. That's pretty good. If you want to actually solve it properly, you have to find the formula, which is what Mallory used. She said L initial equals L final. And L initial is I initial omega initial, right? That's angular momentum, I times omega. And that's equal to I final omega final. And so just looking at this formula, you can see that if I chop this in half, I gotta double this so that it stays the same, right? Just looking at the formula for L. L equals I times omega. If I chop that in half, I gotta double that. That way my L stays the same. Does that make sense?
Wait, if you chop what in half, you have to, oh wait, oh yeah.
If I gets chopped in half, then W, or omega has to double. Okay, so that doesn't require us to think about the energy, but guys, let me write this over here. Omega doubles. And then let me ask you guys a related question. What happens to her rotational kinetic energy? Same question. What happens to her rotational kinetic energy? Does it stay the same? Does it halve? Does it also double? Is it quartered? Or is it quadrupled? All right, guys, let's see your answers. I got a bunch. I got about half of you. Okay. 1, 2, 3. not split. This isn't exactly, but I got about half of you saying this. And then about half of you saying this. Not exactly half, a few people chose different answers, but this is, so the correct answer is C, it doubles.
Bruh.
Can somebody explain?
Give me that.
I can't.
Because, y is half, and the angular velocity is doubled. And then half of 2 squared is 2.
Exactly, remember, guys, this is the mistake, that everyone that chose 5, you were on the right track. You said omega is doubled, so then that should quadruple the kinetic energy, right? But you forgot that I was being halved.
Oh, yeah, right.
So you quadruple it, but then you have it. And so that's what it is.
And then you have it.
This is,
You were on the right track, you guys have the right idea.
This is racist.
this is racist.
This is a race.
Physics is so discriminatory.
This is racist. Is that even a word? Discriminatory?
I don't know, probably not.
You ready for that EOC on there?
All right, so guys,
Oh, so scared. Not really though.
when you are dealing with an object that can rotate, it can have both forms of kinetic energy. And so its total kinetic energy is going to be its linear, the 1/2 mv squared, plus its rotational, 1/2 I omega squared. And the formula isn't necessarily going to be that useful. Again, I never see this calculation come up, but the concept is important because the concept is saying that from now on, our kinetic energy is split into 2 types. Some of it is linear and some of it is rotational.
Watch it come up just because you're over here.
It's going to come up this year just because I said that.
Yeah, I was gonna say, I was like, what?
With my luck, it's coming up.
I've done that before. I had people ask me, there was a formula we didn't cover on the formula sheet. They said, hey, what's this formula mean? I said, don't worry about it, it never comes up. The entire FRQ was based on that formula.
What you're telling us is we should put at least 30 minutes to figure out what all this means.
Yes, you should probably, the fact that I'm telling you this isn't gonna matter means you should probably spend several hours just studying this one slide. Based on my luck.
I mean, we're already at 22 minutes and 36 seconds. Just gotta keep going.
And so,
yeah,
guys,
this is pretty
the
nice.
the kinetic energy is now going to be split if the object is rotated. That's the important thing. That's the important concept here. You're going to split the kinetic energy between the rotational and the linear. Okay, so let's see what that actually means. Let's look at an example. Let's say that I have a ramp. It's a straight ramp at some angle, and I release 2 wheels down the ramp. Wheel A rotates, but it doesn't slide. So it rolls, in other words. Wheel A rolls down the ramp, and wheel B just slides down the ramp with no friction. It doesn't rotate. It just slides down. It would look weird. It would be a wheel that's just sliding without rolling. But it slides down the ramp. If they're both identical in terms of their mass and their radius, which one will have a greater linear velocity at the bottom? Is it wheel A, wheel B, or do they both have the same linear velocity? I'll give you guys a second to process.
I'm putting 2. That was like really. It could be any of the answers, honestly.
Well, I know it's not wheel B because that doesn't make sense.
Wheel B? Yeah, what he's putting wheel B.
All right, guys, see your answers? Oh, wow.
2. Yeah.
Okay, so I'm seeing a split of like 30%, 70%. And then I saw a couple people chose C. The correct answer is B. Can somebody explain why?
No.
No, go for
So
it.
they're both at the top. We learned earlier that the potential energy has to be the same as the kinetic energy, final kinetic energy. Since we haven't learned anything about rotational potential energy, I'm not going to talk about it because I don't know about it. So probably doesn't exist, because I'm stupid, and why would it exist if I don't know about it? But since they have the same final kinetic energy, that means that, if one also has rotational kinetic energy, it has to be subtracted from the final kinetic energy to find the linear kinetic energy.
100%. So what you're saying is at the beginning, you're saying at the beginning they have only potential. At the end they have only kinetic. They both have to have the same amount of kinetic because they both lost the same amount of potential. But one of them is rotating, so its kinetic energy is split, is what you're saying, right?
Yes.
It's split between its rotational energy and its linear. Whereas wheel B, all of that energy is linear. They have the same mass, right? They have the same radius. So if they have the same mass, how can they have one of them have more linear energy? It has to have more velocity, B, has to have greater speed. So wheel B has to be moving faster. Which is, I think, not what most people expect the first time they think about this problem. It seems like the wheel that rolls should be moving faster. Things go faster and faster as they roll down the ramp. The trick here is where I
But does it slide?
it's wheel A sliding without friction is the trick. It's because wheel A has no friction. If it had friction, then it would roll.
It's like a person on ice skates over.
But it has no friction.
Wait, but it doesn't slide, it doesn't move. You don't have.
Wait, so,
It's like a person
Sorry,
on ice
wheel A
skates
does
on
have friction.
ice,
I mean
and a
wheel
person on
B.
roller skates on
Oh.
ice.
It does no friction.
Imagine.
Yeah.
That
In a
person
roller
would be
skate.
doing splits,
That
bro.
person would be straight up.
The reason it doesn't mesh with your kind of knowledge of the world is because you've never seen a frictionless ramp.
Yes, I have.
Yes, I
You
have.
have, I'm sorry. I shouldn't have spoken for you. Some of us have seen a frictionless ramp, but most of us have not.
Have you though?
I own one, it's in my backyard.
Frictionless ramp
Right.
for my motocross.
You gotta go fast.
No, one night I went to sleep, I woke up and there was a frictionless ramp in my backyard. Oh, I hate one of those.
So guys, the very last thing here, and we've looked at this, that worksheet that we did yesterday, you guys already looked at this, we're now just gonna write it down to make it official. Rotational collisions are things that can happen. And in fact, they're more common than linear collisions, because anytime, if you guys think about any time you've ever seen two things collide, they probably, one of them at least started spinning around after the collision, right?
Yeah.
Like, things very rarely just collide directly head on.
They both went
They
through
usually,
each other.
yeah, it's usually like
Kept
off an
riding.
angle, so one of them ends up spinning and rotating. And so a rotational collision is just one where either one of the objects or both of them are initially rotating, or they're rotating after the collision. So there's some rotation.
Kind of like lightning McQueen.
And so the only thing you have to know is that in a linear collision, just like linear collisions, momentum is conserved in a rotational collision. So you can use rotation, you can use momentum to solve a collision that involves rotation. But, just like with linear collisions, collisions do not necessarily conserve mechanical energy. And so, you cannot use energy to solve any problem in which there's a collision, unless you know for a fact, you were told, 100% certainty, that the energy was conserved. You cannot assume. You cannot and should not assume that energy is conserved. Don't apply energy to a collision. Or at least don't apply conservation of energy. In fact, guys, I'm going to tell you a secret right now. You can split the AP test into two types of questions. Questions that can be solved using conservation of energy and collisions. Guys, if you understand conservation of momentum and you understand conservation of energy, That's gonna get you almost entirely through the AP test without needing anything else.
Kinematic.
So we just gotta study those two things.
That's what you should
You open
focus
the
on
AP
studying,
test and
guys.
it's like stoichiometry, chemistry.
If a problem involves a collision, you use conservation of momentum. If it doesn't involve a collision, reach for conservation of energy. That'll probably get you the
Yo,
answer.
send this video to me. Alright?
Let's look at one rotational collision. And this is the, I know we've already looked at this scenario multiple times, but let's look at it one more time just for old time's sake.
They better not be the ring.
It's a red car and a blue car.
So, come over.
Click on gain momentum, right?
Oh. More discs.
So guys, last time we looked at this, it was a lump of clay. But now it's a disc. Same idea though. Same idea.
Oh, no, this is impossible.
I
Two
hate
identical
discs.
discs rotate around their centers in opposite directions with the same magnitude of angular speed.
I'm never listening to a CD again.
Now, notice it says angular speed. It doesn't say they have the same angular velocity. It says they have the same angular speed. The top disc is dropped onto the bottom disc, so they collide and they stick together. Which of the following predictions is correct about the motion of each individual disc after the collision? A, each disc spins with the same final velocity, which is 0, so they're stationary. Each disc spins with a final angular velocity greater than 0, it could be anything. Each disc spins with the same final angular velocity that's greater than 0, but less than the initial velocity. Each disc spins with the same final velocity that is equal to the initial velocity.
It's either 1 or 3.
I feel like because they cancel each other out, right? Because that one's spinning positively and that one's spinning negatively.
It could be D though, cause like,
How would it be
it's
D?
not D. I'm tripping.
How would it be
No,
D?
but when they spin, there's like torque, you know, like, cause they're like. against
So you're
each other.
saying
No.
they're gonna
But there's like a torque.
they're not going to be affected at all. Is what you're
They're
saying.
not. They are going to be affected.
So then it's not D.
No, yeah, I said it's not D. Cancel D out instantly.
You
But
guys
like,
see your
there's gonna be like a
answers?
friction, unless they're frictionless. Are they frictionless?
No, they stick together.
So guys, I see almost everyone is answering the same thing.
Because we're all smart. Except for
The
this
answer is
dude.
A.
Dude, that's, wow.
You just.
The one time physics actually follows basic logic. And I chose
So,
something
can
else.
anyone explain how we get the answer A? Okay, go for it.
Both the angular speeds cancel out when they
Okay.
collide. It's
Okay.
basic algebra.
Yes,
Algebra.
but you have to be a little careful. It's not the speeds that cancel, it's the momentums that cancel. Because
Yeah,
technically-
Kate.
Well, because Kate, think about this, technically speaking, if they weren't identical, right, and they had the same speed, then they would have different momentums. So their speeds would be the same, but they wouldn't cancel in that case, because one of them would have a greater momentum. It's only because the discs are identical that they have the same momentums.
So, if say the top disc was not solid but instead a ring, then this problem would be a little more problematic.
Yes, because if they were not, yes, I like that. So if this was a ring, right, but it had the same velocity, would it have a larger eye or a smaller eye?
Larger eye.
So then would it have a bigger angular momentum or a smaller angular momentum?
Smaller. I mean bigger.
Bigger, okay, so that means that, guys, this system of two discs, you have some, let's see, this is clockwise, that's negative, right?
Yes.
And this was counterclockwise, that's positive. So what you're saying is that this system overall has a little bit more positive momentum than it does negative momentum. So then after they collide, that's still going to be true. But since they're stuck together, that means that that positive momentum means that they have to be spinning counterclockwise. They would be spinning very slowly counterclockwise stuck together. And so that would absolutely change everything if one of them was a ring. That would change our answer for sure. In fact, that would make our answer either this one or this one.
I see where you're going.
And guys, I know that I saw some of you say, but couldn't both of these be true? Because if this one is true, then so is this one. That's a hint, guys. Sometimes College Board does that. They give you two answers that could both be true. That means both of them are wrong. Because you can't, they're gonna ask you to pick one choice. And if there's two correct choices, then that means there's two choices that agree with each other. And those aren't the correct choice.
That moment
College
whenever they
board
say
is some
pick
low.
two and you gotta.
There is that moment when they say pick two.
Wait,
All right, so guys, we have two assignments that you need to complete. There's the assignment you started yesterday on AP Classroom. That one is due by tonight, at midnight. And then there's another assignment on It's Learning that's due by Friday night. And so if you have not finished your AP Classroom assignment, you should try to work on that for the last few minutes. I'm gonna give you guys all an answer. I'm gonna give you one of the answers because I disagree with College Board.
I always disagree.
I know
with
College Board makes the SAT hard and everything. College Board, if you work for College Board, bro, you might as well be friends with Little.
Might as well be seen.
You might as well be friends with Little. Yeah.
Bro, everyone was getting Jones.
Yeah, everyone got John.
So guys, the question is, question three. Question three is, there's a pulley and there's a mass hanging from it. And the mass descends for some time, and they call that time T0. And they want to know what the angular momentum of the system is. And the answer that they say is correct, they claim that answer choice B is correct. With an M
physics
times
shirt.
G times R times T. Now, I'm telling you guys this because I believe that answer choice is not right.
Bro, I'll make it design.
There is no correct answer choice listed among those four choices, so that's the one they want you to pick. What they're doing to get this answer choice is they're saying that the change in angular momentum, delta L, equals torque times delta T. That's impulse, right? Just like force times time, torque times time. Well, they're saying that the torque is mass hanging times G times the radius of the wheel. And then delta T is T0. And I say that this is not right. Because, yeah, this says that the tension, this is saying the tension in the string, right? That's what's creating the torque. They're saying that the tension force is equal to the hanging mass times little g, and that can't be right. Can anybody tell me why? Mallory, right there.
Because otherwise, it wouldn't be moving or accelerating at all.
Yes, if that was true, they wouldn't be moving. They would just be hanging there stationary. Because then this would be balanced. It would be in equilibrium. It would accelerate downwards. So this answer choice can't be right. I don't know why they listed that as the correct choice.
Hey, everybody go vote for my physics t-shirt design. I got Jones. It's my physics t-shirt design. Go vote for it. I got Jones.
Yo, Mr. Jones, we need that reenactment of you in the chair.
Okay, I'll do it just a minute ago. Very quickly. Take 10 minutes.
Alright, let me upload my file. Everybody vote for my t-shirt design. You'll know which one is mine. You'll just know. You know what I'm saying?
Did you create?
I got Jones. Why is there a picture of Steve Waddle in my camera? What if you click submit?
Oh, that was like a selection.
Let me make sure. I got Jones today.
I will walk in here after class. Well, you need to do it.
Not like there's any more notes to be done.
We'll try to look now, but it's not actually.
Gonna have to delete that one.
Oh, yes. There's packing. Yo.
I just heard hacking. Yes, God bless. God. Whose pants are those?
Yes, sir.
Dude, I walked by somebody in the hallway. Some girl was telling this guy, yo, this dude's packaged. And the guy was agreeing. He was like,
Damn right.
bro, yes, he is.
What level of self-confidence is